Hey, this is Mr. Aiden. This is the 2023 AP Chemistry exam that was released on May 1st, 2023. This is free response question number 3. So for all your AP Chemistry needs, if you're a teacher or you're a student, go to MrAiden.com, take a look at AP Chemistry Platinum. So let's get to number 3. Number 3 was all about calcium carbonate. And you can see we have a reaction where calcium carbonate solid is combined with hydrochloric acid to make calcium chloride and carbon dioxide gas and water. And they want a net ionic balanced equation. You can see we don't want to split up calcium carbonate solid because it's a solid, but hydrochloric acid is a strong acid. So we want to put 2H plus for the strong acid, and the calcium chloride does dissociate as well. And so it dissociates into calcium ions and chloride ions. And obviously the chloride ions are spectator ions. You don't want to put them. And so we're going to put calcium plus 2 as a product, calcium or carbon dioxide gas and liquid water. And you can see everything is balanced, the atoms and the charges in my balanced reaction. Well, they took this calcium carbonate, and you can see they did a little experiment where they took different concentrations of hydrochloric acid in different trials. They took different particle sizes, and they found out the time of the reaction. And the first question for B says, why is trial number 5 inconsistent with the data? Well, take a look. The small chunks in trial 5 should have a time of reaction between the fine powder in trial 4 and the large chunks in trial 6. The small chunks have greater amount of reaction surface areas when compared to the large chunks and less reaction surfaces than the fine powder. And this is going to result in more effective collisions, and that is why it is inconsistent in your data. And you can see part C says, based on the reaction conditions and the collisions between the particles, that's a big word right there, particles, which means we want to really take a look at what's happening with the particles. It says, explain the reason for the difference between reaction times of trial 2 and trial 3. So we take a look at trial 2 and trial 3 with the same 1 molar hydrochloric acid, but we have small chunks and large chunks. So we want to really take a look at what these chunk sizes are doing in terms of particles. Trial 2 is small chunks of calcium carbonate, which allows for a greater number of surface collisions with the H plus aqueous particles. This allows for our faster reaction rate time due to the greater number of effective collisions. You're going to have more effective collisions. Whereas in trial 3, which has large chunks, there's less particle collisions, there's less number of surface collisions, and therefore less effective collisions. So in part D, the student is claiming that the reaction is zero order with respect to the hydrochloric acid. So we're going to come back to our data, and we're going to take a look at when does the hydrochloric acid change its concentration. And we're going to keep particle size of calcium carbonate the same. So let's look at trials 1 and 4. We could look at 2 and 5 or 3 and 6, but let's just zero in on 1 and 4. You can see the hydrochloric acid tripled in its concentration, and the reaction time changed. And so we're going to disagree with the student's claim because when we compare trials 1 and 4 and the concentration of H plus triples, the reaction was zero. If the reaction was zero order, the reaction rate wouldn't change. It wouldn't matter. But the reaction rate is shown to increase by about a factor of 3 during these two trials. So it's probably a first order reaction. It's definitely not a zero order. And then we get a little bit of stoichiometry here. And this one probably tripped up some students because you can see the HCl is in excess. It says determine the molarity of the HCl. And there's a big, huge term that the students had to recognize. It says after the reaction is complete. I know a lot of students probably skipped right over that. So we take a look at how much mass of calcium carbonate, because that's our limiting reactant. We have 1 gram of calcium carbonate that is reacting. So 1 gram of calcium carbonate, we divide by calcium carbonate's molar mass, and we get 0.00999 moles of calcium carbonate. Or you could say 0.0100 moles, okay? We're going to take a look at our balanced reaction that we got, and you can see there's, for every 1 mole of calcium carbonate, there's 2 moles being used of the H plus. And so for every 0.01 moles of calcium carbonate, we're going to use 0.0200 moles of HCl. And you can see I'm putting in words like used to make sure to keep everything straight. In trial 2, remember we're only looking at trial 2. In trial 2, we used 1 molar of HCl. We use 50 milliliters of HCl. So we take 1 molar of HCl times 0.05 liters, and that means we had 0.0500 moles of HCl available. That's how much we had. Remember, that was an excess. And so if we want to find out how much we have moles after the reaction is complete, we got to subtract these two numbers, which gives us 0.0300 moles after the reaction is complete. This is what they want to know the concentration of. So we take the 0.0300 moles of HCl, we divide by the liters, and we get 0.600 molar of HCl after the reaction is complete. Well, part F took a look at the temperature at this point. So we're changing to a little bit of a thermotype problem, and you can see as the student measured the time, the temperature was increasing here, which means the temperature, the surroundings, if the temperature is increasing and we're measuring the surroundings, that means the surroundings is absorbing heat, or it's endothermic, which means the reaction system itself is exothermic, or is releasing heat to this surroundings, okay? And so they want to know how much heat did we actually release, which means we're going to use a Q equals MC change in T problem. My mass is 51.0 grams. They gave me that. The specific heat is 4.0 joules per gram degree Celsius, and we find the temperature change, and that means the surroundings is absorbing 142.8 joules of heat, which means if the surroundings are absorbing this heat, the reaction is releasing this heat. It's releasing 142.8 joules, which is part 2, G part 2, and we're dividing by 0.0100 moles because that's how much of the limiting reactant we use. We got to use the limiting reactant there. And for our enthalpy, we get negative 14294 joules per mole, which changes to negative 14.3 kilojoules per mole. And we got to put our negative there because it released heat. The reaction system released heat. Well, that was the 2023 AP Chemistry exam free response question number 3. Number 4 is coming right up. Tune in. Thanks. Bye.